Well, good morning, everyone. Sorry it's going to be a little dark again because I'm filming in the morning, so I apologize that you can't see my face. But for some of you, it's probably a good thing, right? You don't want to see my face anyway. So, Chapter 8, Aquatic Biodiversity. We should move through this one pretty quick. 8.1, what is the general nature of aquatic systems? 8.2, why are marine aquatic systems important? And so we're going to look at setup and some importance, all right? Which in Florida, we depend on the ocean. So, first, saltwater and freshwater aquatic life zones cover 73.2% of the Earth's surface. What is that, 3/4 roughly? Salt is 71%. Freshwater is only 2.2%. Think about that just for a second. When you think about drinking water, bath water, water to put on your lawn, wash your clothes with, 2.2% of the water we have on the planet is fresh water. It's a very small percentage of that total body of water. Referring back to the salt water, 71.2%, or sorry, 71%. Your body is roughly, depending on your male or female, anywhere from 60 to 68% water. So we're roughly the same percentage of water as the Earth is. Ironic? Maybe not. Okay, so life in layers. Let's take each one of these one at a time. Temperature. Temperature we'll look at, especially when we get into the coastal zones, is very important for a variety of reasons. For chemical reactions to take place, they perform better at certain temperatures, and as the oceans warm due to climate change, it is either stopping or slowing down certain chemical reactions. Certain organisms do not like being in incredibly hot water, and when we talk about coral reefs, we'll discuss that in a little more detail. Dissolved oxygen, fish, a host of other organisms in the ocean rely on oxygen just like you do. You have to breathe in the oxygen, and so do these aquatic organisms. So do the aquatic plants. They need oxygen as well. Availability of light, euphotic zones or euphotic zones. Nutrients needed for photosynthesis, and if you remember back to El Nino and La Nina from last unit, we said that El Nino breaks down the upwellings that bring those nutrient-rich cold waters from the bottom of the ocean to the surface for photosynthesis to take place. And La Nina is a strengthening of those winds, which help really drive extra nutrients to the surface of the ocean. And the last one, availability of food. When we talk about the neritic zone in just a few slides, this last one, number 5, will become more apparent. Okay, so life in the aquatic zones. First off, the term plankton that we use, and here is plankton right from your favorite SpongeBob cartoon. Plankton is a generic term meaning any weakly swimming or free-floating organism in the ocean. This includes a lot of different organisms that stay tiny, small, free-floating or weakly swimming organisms. It also includes the larval stage of a host of other organisms. Crabs and lobsters, a lot of your clams and oysters, they begin parts of their body as these very teeny tiny larval creatures that float or weakly swim through the ocean. And then as they get bigger, they descend out of that plankton category into a different creature. So we've got phytoplankton. These are our plants. Zooplankton, drifting animals, they're consumers of these little tiny organisms, but they're eating other small organisms or some of the phytoplankton. And then ultraplankton, which is photosynthetic bacteria in the ocean. And here's, again, a host of different types of organisms that are considered plankton. You can see some small fish. We've got probably some type of water flea right over here. And then these right here are different things known as diatoms, which make their outside skeleton, if you will, out of silica or glass, and they're incredibly beautiful, very, very intricate. And if you look at them up close, you can see just incredible detail. And these diatoms they settle to the bottom, form these diatomaceous earth layers at the bottom of the ocean. And we harvest that, and actually we put it in our toothpaste. When you bite down your toothpaste and you get that crunch, that is the diatoms that we take out of the ocean and put in there, because they're abrasive, softer than your enamel, so it doesn't damage your enamel, but hard enough to get the food off of your teeth. Okay, so we've got nekton, which is a generic term used to describe organisms that are able to swim. Not in the plankton stage anymore, but now we're looking at bigger organisms. So fish, turtles, whales, those are all nectons. Shark, it's a necton. Benthos, or bottom dwellers, are barnacles, oysters, lobsters, crabs that move around the bottom. They may be able to move, they may be stationary. A barnacle is stationary, fixed to whatever substrate it attaches to. We call that sessile, S-E-S-S-I-L-E, sessile. They can't move on their own, but they're on the bottom. And then the lobsters, crabs, they typically don't swim in the way that we think of turtles or whales swimming. Most of the time they move themselves by walking across the bottom of the ocean. So let's look at the marine zones. So we break them up into two broad categories, and they're broken up from there. So we've got coastal zones, we've got open ocean, aka the pelagic zone. So coastal zones are warm, nutrient rich, and they're shallow because they're near the coast. So when you take that coast and you break it apart, we've got the first section, the intertidal zone. So in these intertidal zones, all right, we've got water, salt water moving over the land, right, covering a certain part of the beach, right? And then if you're, again, a sessile organism, perhaps an oyster, you're part of an oyster bed, you're covered in salt water for part of the day. Then the oceans retreat. And now you are exposed to the air. It's dry, there's no water, right? So you have to be able to deal with that constant fluctuation in water level, temperature. And then if you live near an estuary, this intertidal zone would be covered in salt water part of the day, covered in fresh water part of the day, and then covered with brackish water in that intermittent period. So you have to deal with a lot of different changes. From the intertidal zone, we go to the neritic zone. The neritic zone would be the coastline. When you go swimming in the beach, the area you're jumping around in, that's the neritic zone. And that neritic zone extends out, right? Not a certain number of feet, but because the continental shelf is sloped differently at every part of the coast and around the world, what they do is they've determined the end of the neritic zone by a depth. That depth is 500 meters. So if you start at the beach, you put on a dive mask, right, and you start walking into the water, and you just keep walking and walking and walking. The moment you reach a depth of 500 meters, you are no longer in the coast or neritic zone. You have now become part of the open ocean or the pelagic zone. So what's important about the neritic zone? 10% of the ocean, right, is part of this coastline, just 10%. The other 90% is considered part of that open ocean zone. However, 90% of marine species live all or part of their life in this coastal zone. So it is of utmost importance that we protect this zone and the different habitats that are there, which coral reefs is a very important part, and we'll get to coral in a couple more lectures. But 90% of marine species spend all or part of their life there. Very important to take care of. And they have a high net primary productivity because it's warm, lots of organisms there, right? So this is where a lot of your plankton might be. And it's very nutrient rich. So all of these organisms that form the base of the food chain there have everything they need to start that food chain and get it kick-started. All right, so now we move out into the open ocean. So again, it begins where the continental shelf ends at a depth of 500 meters. That is considered the end of the continental shelf. So we start at the euphotic zone. So that is the surface of the ocean area that gets sufficient light for photosynthetic activity. So it extends down to a certain depth based on clarity. Again, it's determined based on how much light can get through a certain part of that ocean. The next is the bathyal zone. Very dimly lit. If you're photosynthetic, you don't hang out here. Not enough light for that. If you're a creature that lives in the abyss, you probably go into the bathyal zone to hunt, right? Because it's not bright enough to really bother you, but there's enough light to see prey, to move around. So from the bathyal zone, you then go into the abyss, which everyone knows is the bottom portion of that of the ocean where that water level is. It is aphotic, meaning no light gets to it, so it's dark. So these are things where you have, from Finding Nemo, the anglerfish that has that weird little light antenna at the front that it uses to lure in fish. You would find that guy in the abyss. Estuaries where salt and freshwater meet. This is part of that intertidal zone moving up into the wetlands on the coast. So it includes rivers, miles, inlets, bays, sounds, salt marshes, mangrove forests. Adaptations to organisms here, you have to be able to deal with changes in temperature, from the different temperatures from being covered in water to being exposed to air, salinity, salt water coming in at high tide, then fresh water rolling over you during low tide, and then turbidity. Turbidity is a measure of clarity, how well you can see through the water. And as that tide is changing, coming in and out, it comes up, right? It covers you with some sand as the rivers are coming down from the mountains, maybe bringing sand. So it may be very turbid at some points and then very calm and clear at other points. Mangrove forests found along the coastlines in tropical and subtropical areas. We've got two different types. We have red and black mangroves here in Florida. The black mangroves are the ones that have those little tiny leaves that stick out of the water, right, out of the sand, and you see all those little spikes everywhere. That's for gas exchange. That's why they have those spikes coming out of the sand. This is a red mangrove, right, and these little legs right here are like little fingers, and they're very important because they reach out and they hold on to all of that sand, right, and they help keep that coastline in place. They're very important along the perimeter of dunes, right, because they hold on to the sand and prevent those dunes from washing away so quickly. And they form this little maze here where lots of little organisms, crabs, fish, they find habitat in there, and it's a refuge. It's a safe haven from the bigger fish because they can't wiggle their way through there. Estuaries are important. They're plants. So like all plants, they help absorb nutrients as it's coming. Imagine all this fresh water that gets pumped out towards the oceans whenever it rains and there's a storm event. Well, without these plants there, these wetlands, to absorb those nutrients, there'd be far more nitrogen and potassium and phosphorus going out into the oceans than we already have. And that would lead to even more algae blooms than we already have. It reduces stormwater damage, again, by protecting that coastline, reducing the quantity of erosion at each storm event. And it provides food, habitat, and nursery site for many aquatic organisms. A great place to go kayaking is these mangrove forests. Here is a estuary marsh, and then this is the Indian River Lagoon, which is a estuary. This is a sand dune. Is there? Oh, I thought there was a title across there. So what this is a cross section through a sand dune or a barrier island. Barrier islands, we love as humans to build on them because they are at the beach, right? So what you'll notice is the older part of the dune that has tall trees, right, is where we usually do the building. The problem with building on sand dunes and barrier islands specifically is that they are made by nature to move, to shift, to change. So what happens is we build there, we find that, oh no, the sand is moving out from away from our buildings. We better add more sand. We better protect these shoreline buildings. Well, nature never meant that barrier island to stay there. It is going to move. And eventually we have to decide, are we going to continually add more sand to this dune, or just let these buildings go because these things are designed by nature to move and to change. Now if you look at this cross section, what do you notice as you move from this side to this side? It's a form of what? Let's see if you get it. It's the third bullet right here that I just realized was there. But yes, succession. So just like primary succession that we looked at in one of the last units, we've got succession taking place across the dunes. The newer portions of the dunes have the smaller plants. As you move towards the old dune at the back of it, you get the tall trees that are settled and established on the backside of the dune. That is the end of this PowerPoint. Thank you for coming.